Welcome back, class. We're continuing with Whitlock Schluter Chapter 7, Binomial Probability Distribution. We just derived its formula, and now we want to use it a little bit. Okay, so properties of the binomial probability distribution. I'm going to go ahead and hit these at the beginning, and then we'll get into it. Hopefully you'll see why. The expected value is the mean, and we always denote the population mean with the Greek letter mu. Okay. However, cool thing is the mu for the binomial distribution is NP. The variance we always denote with sigma squared. That turns out to be n times p times 1 minus p. And we're not going to derive that. I'm going to give a little intuition here in a moment. The standard deviation then, of course, is NP 1 minus p. Okay, so just for interest's sake, let's jump back to the binomial example that we did here, where we had n27 and we had p 0.25. Then the mean, I can just put this mu, is 6.75. Okay, and then let's do sigma square root of 27 times 0.25 times 0.75. Okay, 2.25. So that's handy. Now let's get to the original graph that we wanted. So we do 0.25 and replot. Okay, there's the original one right here. Now the mean 6.75. Notice that baby fits us pretty much right in here where these two high bars are. And then the standard deviation is 2.25. So if you take that 6, thinking in confidence interval terms from a couple chapters ago, go 2 confidence intervals back. That's going to take us 4.5 back, somewhere in here. And then 2 up. That's going to take us somewhere up here. And is that about 75% of the data? Looks like it. I'm not going to do that exact result right now, but it's a ballpark to feel what's going on. Okay, now let's use it here. Okay, sex of my children. If we have the 3-kid case, I've got the results just written out here, so we'll just go ahead and kind of poke at them. The formula you have written down there, so we have n factorial on top, and then x. If x is 0, I'm going to plug in the 0 here, boom. Here's the n. So keeping in mind n is right here. Okay. So x is 0. P was 0.5, so that goes in. 1 minus p is here. And then we have n minus x, which was 3 minus 0. Now, it's a good time to do this on your calculator. It's going to be relatively straightforward because all these, it turns out, are just 0.5 cubed. So it doesn't matter. You have 0.5 in both groups. So that part's easy. And then the task is just to calculate these. So, for example, 3 factorial over 2 factorial 1 factorial is 3 times 2 factorial. And then you have a 2 factorial here. 1 is just 1. So cancel, cancel. We're going to get 3. And then, of course, 0.5 cubed is 0.125. So 3 times 0.125, sure enough, gives me this. Otherwise, there's a 1 in front, so I'm going to get this. Okay, that one's covered. Now, let's go to a second example. I've got ESP incidence. So Jane Doe claims to possess ESP. She says she can guess more often than not the outcome of a flip of a balanced coin in another room. Okay, so you put Jane Doe to the test and flip 3 times. Okay, if she doesn't have ESP, then what's the distribution of her correct guesses? Well, we already know the answer. That would be this exact distribution right here. Boom, no ESP, 50-50 on the coin toss. Okay, done. Okay. Now, let's suppose that she does have ESP and she's at 0.75 probability of success. So, if we do that, let's see, this one says it's done above. If we do that, then we're going to have to come down here. We'd like to make a note in passing, though. The expected number of correct guesses of Jane. Well, let's think about it. If she has 3 guesses and she has a 50% chance on each, then it seems reasonable to take 50% of 3, which is 1.5. That's just the formula for the mean. It's simply that intuitive approach that we just mentioned. Okay. Okay. So for standard deviation, we're going to go sigma equals np1 minus p square root, which is square root of 3.5.5, 1 minus 0.5. And I think I have that somewhere. 0.87. Okay, so we immediately have these parameters for this distribution. Now let's compare it with Jane Doe's second shot here. All right, I've got all these values worked out. Let's go ahead and do one of them. We'll do probability that x equals 2. And when I plug in, n is 3. X is 2, so we got 3 factorial over 2 factorial times 1 factorial. That's n minus x. Probability now is 0.75. Okay, x is 2, so that's a squared. I only have 1 fail, so that's 0.25. And go ahead and run the calculation to confirm 0.422. Okay, now the mean is 2.25. That is 3 times 0.75. Standard deviation is 0.75, which is acute 3 times 0.75 times 0.25 square root. And so we can see that the mean is higher. It's 2.25 versus 1.5. And the standard deviation here is a little bit smaller of those two distributions. And we could plot those on R if we wanted to take a look at the two of them. Let me go ahead and do that right now. There it is. Ah, the miracle of this screencast technology. Very cool. So if you look at the two of these guys, you can see we're clearly askew left compared to a symmetric. Mean is 1.5, mean was 2.25, so that's popping in here. Okay, great.
Okay, let's do a little more realistic example now. 2.3, genotype. Suppose 90% of the offspring of a certain insect population have genotype AA. Okay? Now, we've got 20 randomly selected insects. What's the probability that at least 18 of them have genotype AA? You can see how this might apply in a biological context. So, first of all, we want to see, is this binomial? All right, well, first of all, we need the 3 conditions. So the first condition is, do we have this fixed sample size? Yeah, what is it? It's 20. Are the observations independent? Okay. So independent. Well, when we say 20 randomly selected, then randomly selected is going to get us yes. Okay. Other ways to get independence, but that is the most common. Okay. And then is each trial have the same probabilities of success? So probability of success, we're going to define that as genotype AA. So probability of AA, that is 90%. Okay. So we assume that for a particular insect, there's a 90% probability that they've got genotype AA. They all have that now. Based upon my randomization procedure, we're good to go. We're binomial. Okay, so we can then write X is binomial with parameters n equals 20 and p equals 0.18, excuse me, 0.9. Okay, so question. What's the probability that we have 18 or more insects with genotype AA? Boom. This is the statement, greater than or equal to 18. That gives us 18, 19, and 20. So we have 3 individual cases. 18 is written out for us. Let's go to 19. Okay, we got 20 factorial over 19 factorial, 1 factorial, times 0.9 to the x power, which x is 19. So put a 19 here. And then we're going to have 1 minus 0.9, which is 0.1, to the n minus x power, which is 1. Now, go ahead and check your calculator on that. It should get 0.2702. And good to go on that. For 20, that one's going to get us 0.1216. Go ahead and check that one. Now then, when we plug in for the original 3, we'll just add those 3 together, and we get 67.6% probability. To do that on our studio very easily, we could just go D binom, and I'm only interested in 18 to 20, so I'm just going to focus in on those. The colon says in between. Size is 20, that's my n, and then probability was 0.9. So I run that, boom, those are the 3 numbers that I also got. Okay, so 67% chance, that's pretty good. Might not be nearly as high as you thought. After all, we would expect, since, let's see, the expected value is, it's NP, so that's 20 times 0.9, it's 18. So we're expecting to get 18 of them. The probability that we get 18, 19, or 20 is only 67%. That may be interesting. But it's because there's plenty of chances to get the other possibilities. So the standard deviation, when we run that calculation, is 1.3416. Okay, so we've got our mean standard deviation, and that concludes our hypothesis test, our binomial probability distribution example.